So some of you have asked for some reviews on the gas laws for Module 12 before the test. So I'm going to be going over the gas laws and conservation practice sheet that I gave you to help review. The first problem has a chart that listed pressure, volume, temperature, moles, and mass of nitrous oxide, which is laughing gas. So the first thing we have to think about is the units that we want to have whenever we're using the ideal gas law. And of course the ideal gas law is commonly known as PIV-NERT. So we want our pressures to be in atmospheres, our volumes to be in liters, our temperatures to be in Kelvin, our moles to be in moles, and our mass to be in grams. So if we look at the first one, we're given 250 atmospheres, we're given temperature in Celsius, and we have the mass of nitrous oxide. So the first thing we always have to do is convert our mass to moles. So we find out what the atomic mass of nitrous oxide is, and it is nitrogen is 14 plus oxygen is 16, so it's 44 grams in every mole of nitrous oxide. So we can convert that by dividing 32 by the atomic mass of 44, and we get that it's 0.73 moles of nitrous oxide there. And we can use our ideal gas law equation of PIV-NERT to solve for the volume. So if we have our equation PIV-NERT, we can convert that to solve for volume by dividing both sides by pressure. So substituting in there, we have to change our temperature, so we know our temperature is Celsius plus 273.15, and that will equal Kelvin. So we can solve for volume. We have 0.73 moles times R, which is 0.0821 liter atmospheres per mole Kelvin, times the temperature of 273 Kelvin, divided by 250 atmospheres. We plug all that into our calculator, and we determine that we have 6.5 liter volume for the volume of the gas nitrous oxide given these conditions. Now the next line says that we change our conditions. We're given that we have a much smaller volume at a much higher temperature, and we also have a different mass. So we have to work with our equation again to solve for that. We want to check our units. We want to convert milliliters to liters, and so we know that there's 1,000 milliliters in a liter, so we want to convert this way, 1, 2, 3, so we have 0.075 liters of that. We know that we want to add 273 to our temperature to get it in Kelvin, and we have kilograms. We know there's 1,000 grams in every kilogram, so we'll move our decimal place this way to get grams, and then we need, of course, our moles. We have our mass, and it's the same mass as above, so we can divide by 44 grams per mole, and we get 8.75 moles. And we can use our same equation, our PIV-NERT. This time we're solving for the pressure, so we're going to divide by the volume. So we will put these volumes in here. We have 8.75 moles. Our R remains the same, and our temperature increases to 303 degrees Kelvin, and our volume is 0.075 liters. So we solve for that, and we get that it is 2,902 atmospheres. And we think to ourselves, is that accurate? Our volume has gone way far down, so we know according to P1V1 equals P2V2, if our volume goes down, our pressure will go up. That's true. So even though our temperature has gone up, We know that when we increase temperature, the pressure also goes up. So our pressure has gone up quite a bit, and so that sounds reasonable. But of course, we want the units to be in millimeters of mercury, it asks for, instead of atmospheres. So we're going to convert our 2,902 atmospheres to millimeters of mercury. And we know that there's 760 millimeters of mercury in every atmosphere. And so we multiply those together, and we get 2.21 times 10 to the 6th millimeters of mercury. You see that? There we go. Okay, so once again, we're going to change our conditions for our gas of nitrous oxide, and we're changing to millimeters of mercury. We have 6 liters, we have 100 degrees C, and we have no moles or mass. So we have to convert our millimeters of mercury to atmospheres because of our R. We're always going to use the R that has atmospheres in it, so we're always going to change our units to atmospheres. So we know that we have 768 millimeters of mercury, and we know that when we have 760 millimeters of mercury, that is 1 atmosphere. So using that conversion, we find that we have 1.01 atmospheres. We divide. Our liters are good. Our temperature has to be converted to Kelvin, so we have to get up, we add the 273, so 373 degrees K. And we use again our Pivnert to solve for our moles, and then we can convert to our mass. So we know we're solving for moles. So if we have PV equals nRT, we want to solve for moles. We're going to divide both sides by RT to get our moles alone. And Bree, if you want to rewrite this, as you like your equal sign over there, it will be moles equals PV over RT. Then we substitute in what we know. We know that our pressure is 101 atmospheres times our volume of 6 liters divided by R, moles Kelvin, and our temperature, which is 373 Kelvin. And so working all that together, we know that we end up with 0.19 moles. So we still have a blank space on our chart. We want to convert 0.19 moles of nitrous oxide to mass. So instead of dividing by mass this time, we're going to multiply by mass to get rid of our moles. And we find that we have 8.5 grams of nitrous oxide when we have these conditions. And so our final row of the chart, which I've kind of written all over, says that we have 195 kilopascals, 2.75 liters, and we have 45 grams of nitrous oxide. So once again, we want to check our units. Kilopascals needs to convert to atmospheres. And so we know that when we have 195 kilopascals, we know that we have 101.325 kilopascals in an atmosphere, and so that converts to 1.92 atmospheres, and we have our units in liters. We do not have a temperature, but we do have a mass. So we have a mass of 45 grams. So we'll go back to converting as we did up here. 45 grams divided by 44 grams in a mole, and we end up with 1.02 moles of nitrous oxide. So we have moles now, we have our volume and our pressure, and we have R, so we're going to be solving for temperature this time. So when we have our equation, Vibnert, we want to solve for temperature, so we want to divide both sides by N and R to find the temperature. So as we do that, we plug in our 1.92 atmospheres times our volume of 2.75 liters divided by 1.02 moles and our R, which is 0.0821 liter atmospheres per moles Kelvin. And when you do all the math, it turns out that we have a temperature of 63 Kelvin. So that's how we use our ideal gas laws, given masses and pressures and temperatures, to solve for all of those. I think that hit solving for each variable, so you should be comfortable rearranging your equations to solve for each one of those.